Welcome everyone for High Performance Computing Advanced Scientific Computing. Today we have our practical lecture 2.1 all about MPI messages, collectives, communicators, Cartesian communicators in the end. So it's quite a, let's say, comprehensive lecture that complements also really what we basically have learned the last time. So let's go a little bit into this, but here we see some conceptual aspects of the message passing interface. And this is something what I will also demonstrate a lot today. We will cover a little bit the MPI environment. That is very important, do an hello world MPI. But we'll quickly learn also differences today, what we had also the last time. So MPI can be about message exchanges, which we talk about MPI point-to-point communication here, from one memory space to the other, basically from another processor. Hence, remember, we're talking about distributed memory programming here. Then we had also these interesting collectives, which have some functionality within it and also enables us to have inherent scalability. And I will demonstrate this again today. For instance, MPI broadcast is very often used to really broadcast information to all other processors within basically the same communicator, and it's not clear necessarily how that is. We started this a little bit last time, but I will show you again the demonstrations. And then we'll be getting much more clearer. Instead of broadcast, you can have also gather and scatter. You see here scatter an array to many other processors, gather data from many other processors. And then also we had this interesting addition here that you have in terms of having, for instance, a global sum or so that you can also put when you do, let's say, these operations. And we will come to some examples today. I motivated a bit MPI with one of these interesting, applications of, glacier calving here. If you look a little bit into this paper, if you want, then you can see some interesting ideas how MPI can be used. And you see here out of this paper, one key idea that there's some serial processing done to generate a mesh, how it looks like, the situation with the glacier and so on. And then we have different solvers that actually deal with the problem in different ways, also in different parallel ways. You see 16 cores are used for the ELMA solver here, which then is an input to some transformation package that we basically just now, will transform to HIDEM. And with this, we have the problem that we want to run more cores to have this. Hence, we need more basically, more CPU resources really. So in this sense, this is something where MPI is good for. It's parallel codes. We can use these different cores in parallel and should be a real application example for you. So what we also had then was starting with some parallel programming basics. I can back to this a lot today, so I will not spend very much time. You can think that the same executable will be executed 4 times. So the question will be how we can differentiate if we run on different processors, and this is something what we call the MPI rank. Hence, there's a communicator, and every, let's say, process that is initiated from the MPI environment gets a dedicated rank, and with this rank, I can really differentiate between these different processes. And I can create subgroups, different groups, and so basically here we talk about that we can use this in communications, these ranks, and of course also then when we have the same source code, we also want to have different parts of the source code executed, right? This is also not directly obvious to you. We will see how that materializes when I give you also some examples. So finally, what we had the last time was also then the idea of MPI-I/O. Here we react a little bit also to student feedback to the course. There were lots of repetitions, so we have a bit, let's say, compressed some of the MPI materials. And one of the points here is now also given that we put in new attractive topics to the course, that we don't have really very much, let's say, practicals on MPI-I/O anymore, But still, it's an important topic. Think about that you have a parallel file system. We learned a little bit about this the last time, and you have this MPI-AO that can really leverage this. So really treat this concurrent access to files as a common event so that all these different processes can write at the same time within one file, which is a binary file usually accessible via one, let's say, high-level I/O library. I gave you HDF5, I think, as an example last time, for instance, which is then also used in applications. Hence, let's come a little bit now finally to the lecture 2.1, which supports basically the lecture we had the last time with practical examples. So we will go back to the idea of having really C-based MPI programs, distributed memory, parallel programming. We will understand then from C how we can get to MPI programs, essentially adding this parallel environment with MPI code parts. And then we start with message passing, although the very first application that we really will use will not do message passing, but just use MPI and ranks. However, then we quickly understand ping pong as a way of point-to-point communication versus collective operations, where I give you a little bit an insight on broadcast. Then, of course, with all of this, we should understand a bit the situation, how it works together with a scheduler again, right? Remember what we have learned from the beginning from the course, and also how this is now allocated on computing resources. The second part will be then a bit more advanced topics of MPI. Also here we react to some, let's say, student feedback and also YouTube listeners that said, let's bring some things together. So this lecture here will be much more, let's say, comprehensive material. So there's a little bit more in it than having, let's say, more repetitions, what we had here in the past here and there. But the speed should be still, let's say, moderate so that you can, let's say, follow quite good. And then we will start with the second part, really with the blocking versus non-blocking communication. This is not clear. We will see how that materializes when we talk about this I send and I receive, and then why we have to wait and so on. And then an interesting topic is a very application oriented is then this Cartesian communicator dimensions and shifts programming. This reflects a lot also on something we will have in lecture 3, so parallel programming a bit more conceptually understood again, but we had already the example the last couple of lectures where we had the ocean, right, where we said, okay, let's make a Cartesian grid over the ocean when we want to have waves propagated from left to right. So how I actually implement this, or how I do this boat that we had as an example, how I actually do in a simulation a boat that is actually going from grid to grid to grid part. So this is something what we also will do in the second part today, and of course some application examples of this non-blocking combined with this Cartesian communicator on Elia to give you practical examples. After that, you really have a good idea of complex aspects of parallel programming with MPI. So you can potter off and do your first MPI programs. You will see it's not so trivial. We start very trivial, but quickly will advance by using MPI ranks, using collectives, and then quickly also thinking about non-blocking communication and Cartesian communicators, which are getting then really to complex materials. And you will see how the source code will getting a bit more complex and complex, but this is then basically the foundation how scientific domain applications work in many cases, right? Especially when you think the Cartesian communicator, which is often used. Then with this, you should be really able then to, start parallel programs with MPI, and you will do by reusing this in our assignment 1 a little bit. So let's get started with a more practical lecture here on MPI. Hence, I will switch again, as you know already, to my SSH client a lot. So let's connect first on Elia. By now, I also will not explain these things too much anymore because we have done this all the time, essentially in the last couple of lectures. Remember, we had also to put the private key into place, which is a very important part. Usually password protected. Here it's probably already in because I had already the couple of the material tested before. While we wait for Elia to give us a login, just to basically think about what I said also in the idea of the lecture today. We have this point-to-point, and then later we will talk about collectives. When you have a point-to-point communication, now we see the first time really source code. There's basically the MPI header, which we have to add to our normal hello world that we had. And then there's this interesting MPI init and MPI finalize, which determines then really the region where basically there is an MPI parallel environment. And there's sort of two important and often used commands that you see here, MPI com size and MPI com rank. And these are important to understand in a given communicator, which is for us now in the beginning, the MPI com world, so the kind of world of all processes, right? So we have there a size, which is here 10 from 0 till 9. And then the size would be then equal for all the same because we have 10 processes here. But however, rank will be very unique. It is a very important key, let's say, variable for us that we always have to initialize via this MPI environment to later on show also differences. And you see how that works. Hello world, I am someone out of someone. Hence, we'd say I am rank out of size, right? So this is something what we want to practically now understand. If Elia has now finished the log on, we can go into some practice. So we do here a higher font size. We go to our HPC course in spring and the MPI. And there we have already a hello MPI. If you remember now, we're leaving the space from the typical hello world that I basically had in practical lecture 1.1. But here we add now this interesting size and rank information that we want to give out in order to prove if we really work in parallel. Now you remember also what we had in terms of compiling. I will also not make a bigger message here. You see a little bit, I can go to the history here to make it simple. That we want to compile. This is another one, but in order to compile, we want also to do this module load, right? So that we had described last time, so that we are sure that the right MPI implementation is loaded. And now we can say, okay, let's compile with MPICC minus output, and we want to have, or let's maybe we should remove the hello right first, so that you see that it's really working. So MPICC minus O hello on hello.c. Then we have our executable, and the job script is also no magic. By now you know this. We do the hello, and we load the module load environment, and we want to execute it on 4, which is sort of important because this now will determine if we can really give out, let's say, 4 of this. So when I now say sbatch submit script, then we get a job ID. The job is running so quickly that we don't even see it in our queue. With SQ, you can see the queue usually, but we see with the same job ID, which is now, you remember, a very important part for us. There's an output already, and when we look into this, you will see an interesting statement that although the same source code was executed, it is literally true that through the rank, you see that here we get different ranks for each of the execution of the source code. And this enables us many different things, right? I mean, we can also do the following interesting thing, that we also don't program it actually for processes, right? So now we say task per node 8, and I don't need to change the executable because it's inherently scalable, as we said in the lecture 2 already. That's one of the goal of programming MPI usually. So you see it's so quick with our outcome here. We can look into it, and then no surprises probably. Now we have 8 processes, and the rank is very unique for each of one, starting from 0 to 7 with 8. Now, a very trivial example in a way that is also what you see here on the slides for you to better understand it, what I explained, the hello world, the init, the finalize, making the environment happen. Very important is to get the size and rank, and you can see that almost all MPI programs, I would say, have the size and rank. This kind of initialization of these, they may be called differently, but basically the variable can be, of course, named differently as a typical C program, but you will find that this information is usually quite needed. We have used the compiler. We, of course, had first to run and load the module here in order to compile properly. And basically, that is all what you have seen. When I was executing then with MPI run and the batch script, I could steer with a batch script 4 or 8 or 12, maybe I want, and then I would be scalable. So that's what we have done. And you have basically understood by now, I hope, a lot how this scheduling works. But let us come now to something more, because in one respect, we have done now this interesting hello, but you also understand that this is a parallel approach. And, you know, this means now we want to also do some message exchanges, hence the name message passing interface, right? A standard. The Hello MPI that we had now was absolutely not a message exchange, right? It was just rank information given out and size information giving out. So now we want to switch a little bit the perspective and want to see what's happening if I do a point-to-point communication or two of them using something called ping pong. So here we have the same that we had in lecture 2, the more conceptual idea how it works with a serial environment before and after. We have the MPI environment, and in this MPI environment, we use these different processors that are available, but they all have their own memory, as you already know from lecture 2. Hence, we talk about distributed memory. We have to have message exchanges, right, in order to communicate between the different processors. Here's a simplified idea how that works. The real idea I also was presenting last time is then really the idea of, you know, making some buffer where you have some information in ready to receive when you send it over the wire, and then maybe can even update your own variable with it. So let's do this in practice again. I will go back to this. There's another application example for you. As I said, it's a bit more condensed than usually in a couple of years, but this is not a big problem. Let's look into ping pong. And I think the name already suggests what's happening. We have here our MPI init, we have our MPI finalize. That's important. We had the initialization of these interesting number of tasks or ranks. So this is equal to the number of processes that I have here available in the MPI.com world. And here you see now how beautiful this works with rank 0 and rank 1. Right? Given now that this is the same source code executed twice, I can steer the application logic with it. So I say, if you rank 0, your destination should be 1, so sending from 0 to 1. But if you rank 1, and this is now basically sort of the pong, right? Then, we have a ping pong where, the first one is sending and the second one is, receiving the ping. And then the second one is receiving and waiting for the pong to happen, which is then initialized by rank 1 to do the pong. You see also with this that this point-to-point communication is now an important factor, that someone has to listen, right? So think about a ball that you have in some game like basketball and you pass the ball to another player. If the other player is not listening to the ball, is not paying attention that he might get the ball, the message will not work, or in other words, the ball will not really land in its arms, and instead will maybe knock his nose or something. So here's a very important aspect of it, that every send needs a corresponding receive from another processor. Hence, we can determine this via the different rank. And then this is the ping implementation, which sort of needs two source code lines here. Then the pong is, of course, the reverse, given on the identity once you have done this. And we do this a little bit here with some chars. That's not so important to understand for you exactly, but we want to send something, of course, from the destination, from the source that we have here. And then essentially, the source will be later the one that sends the pong. Hence, the destination for the ping is 1, and source is also then, of course, the origin, so to speak, of the pong. Hence, both needs to be 1. And here's the inverse. Of course, we get first from the source a ping, and then I want to send the pong back to the source, which is also then essentially the 0. And we want to here use this MPI get count to really understand how many chars we're going over the wire, and print that out a little bit in a small statement here. Tags can be used to have different messages also tagged, as the name suggests. So this is also something where usually you have there quite some yeah, possibility really to understand the differences in all of these, let's say, messages, because here we do just a simple ping pong, right? And for the sake of time, I think I have here on the slides, of course, that you need to compile it. And of course, what I have here, I have also, described to you all what I basically just said in the messages. And I would now skip a little bit here this compilation process. You can imagine you need to do the same, MPICC and stuff like this in order to do so. And we don't need to do this now. We have already this executable here. You see the ping pong, and we look a little bit into the job script. Also here, no big surprises. We need 2 tasks per node. But I also want to stimulate you a little bit to this nodes and tasks. And you know that already a little bit what we had in the earlier lectures. So Utun had 4 nodes, and each of them have different processes that we can use. Hence, when I do it like this, I would say now SBatch submit ping pong. The job ID in the SQ, we probably are so quick that it has been already a ping pong performed. Also, no big surprise in such a little job. You see here the job ID, this is equivalent to the one just executed. So let's have a look on it in order to understand what's inside. And here received 1 char from task 0 with tag 1, and then received 1 char from task 1 with tag 1. So this is the ping and the pong, right? So this is exactly from the simple source code that we have seen the idea. Now, interesting might be the following in this context, because we can see, of course, that, firstly with a partition Utun, that it has for compute nodes. You see here nodes compute 1 to 4, right? So that means, in other words, when we want to analyze now how the job was run, we can do this S control and then something like show job ID, very, much output. And then we go now with the job ID. And this is now something we had executed here. And this gives us now a good understanding. It's exactly what we requested. Number of nodes was 1, number of CPUs was 2. So no surprise there. It was running on compute 1 node. Now, interesting enough, again, also to show the independence again from the source code, we can do now the following and do, let's say, 2 nodes. And on each of the nodes, I want just 1 task. It is, so to speak, a waste now what we do. The waste is because we basically use now two nodes and just with, each one little task. And this would be not needed. Again, the SQ is by far too quick. But if you now go into the S control, let's say, first we want to verify if we get some output, right? So more, this time we had our 71. So, sorry, that was, of course, we want here the whole file, right? You see that was working as well. But the difference now from this interesting job, what we did is, and this is good for you to understand, show job ID, minus DD. When we now look into this, we will see that actually this was executed now on 2 nodes, on the compute and 1 and 2. So, and here is compute 1, and we have basically 2 complete nodes. And with this, basically we're, let's say, wasting, in a sense, resources, because we just needed 2 tasks really to execute this little program. Good, let's go back and essentially think about that this was now point-to-point communication. I was also in earlier lectures already pointing to this interesting thing that you see here, the ganglia report that you can have and see the compute node loads and so on. I gave the link here. In the sake of time, I also don't really will talk about this very much. It's sort of more additional information right here. This is also what I presented to you, to the output, playing a little bit with the nodes and tasks, so to understand that this is different things. And I put you this here also on the slide so that you see, in the one hand is a nodes, right? 2 nodes, each 1 job, and 1 node with 2 jobs, but essentially use 2 nodes, which is not really necessary. And these are different things, although just small parameters, and both work but we really have to in HPC more fine-grained and understand what we're doing in terms of computing when we have especially also, let's say, larger applications. Speaking of large applications, it's time for us to move ahead. This is, let's say, the area of collective communication now. So we had point-to-point with ping pong, very simple. Now collective communication enables us, as I also repeated basically in the beginning of the lecture, it is enabling us really to have, let's say, all processors involved that are part of one communicator. So much more easier than always writing for loops, right? For instance, in order to, get communication done to all of them. Today, I will show you just a little bit the MPI broadcast, right? And we will start to really identify again the idea with ranks, right? So this is here on this side. This is the same that we already had before, but here we do a buffer, which is important for us to basically have then some information inside that we want to fill and what we want to broadcast then, let's say, for one processor. And this would be, let's say, source count and buffer is uninitialized, as you see, right? It's basically just here. And only if rank equals source, essentially then the buffer is initialized. And this would mean if, let's say, the communication will not take place that we will implement here in between, when we give this out, only one processor, the source 0, which would be our rank 0, of course, will have filled the buffer. That means, in other words, we want to have 4 times this output, for example, of saying each of the ranks, but here we want to now send this filled buffer that we have actually just filled here with for loop, very simple with E. So from 0 to, let's say, the number is count here, so we have 4, so we assume from 0 to 3. Hence, very important to now use only one source code line, the broadcast, where you can actually have now the count of the information go over the line, what type it is, the MPI int, which source it is, and basically the whole world of communicators. Hence, you see no destination. The destination is clear from this MPI-com world, which will address every processor inside here, right? And this is now an important part because many, and also when we looked at some source code before, for instance, in this paper, where, let's say, machine learning experts have created a parallel version of a support vector machine, very sweet material. It's a good machine learning algorithm, but the parallel version was a little bit interesting. It was not so good MPI, if you want, right? There were some improvements because there was an iterative send and receive often in the loops instead of just using collectives, for instance. And the collectives are really well implemented, so it also is a sort of let's say, performance aspect to it to really use them in production, in applications a lot. So let's see how that works now when we do this again in practice. So leaving the space again a little bit here. We had ping pong. Now let's do the broadcast example. And here again, the broadcast.c is essentially what I already said, only for the source we initialize. And then we have the broadcast that sends this initialized buffer to everyone else in MPI-com world. And everyone, remember that this source code that you see here will be 4 times executed, right? 4 times executed with 4 processors because we want to do so. And we can steer this with this job script and say, as you see here, 4 times, right? Task per node 4. And the MPI run will make sure that I executed 4 times. So when I now SBatch this, again, I skip here the compilation aspect. I think it's for all of you clear that normally, you have to make sure they have the model environment, you have to execute or the MPI-CC. And we don't do this here again and again because it would be also more repetition. So instead, we got the job ID here. And so let's look what happened when we now go into this. We see now the expected outcome that essentially everyone received the buffer, everyone in terms of, basically the other ranks that are now can give out the buffer without any initialization. It would look very weird numbers if see a little bit But here it's very clear that this 0, 1, 2, 3 has been going basically via the broadcast command to everyone else, and then was influencing how the buffer can be. Right, so this is all in a way simple. More interesting for you maybe also to understand is now the inherent scalability, right? So see what I do now. I basically improve now our job script and say, well, let's do 8 processes or tasks per node, basically, if you be precise. And I don't change the source code again, right? So, and the source code itself was done in a way that it was really scalable. If you come back a bit through the slides here, for instance, you see we basically can say that we have this buffer that we have and the count that we have, but not how many players we have, right? So how many really are in the processors or so. And this is now the interesting thing, which of course comes through the MPI environment, right? Where when I do now SBatch submit broadcast, and again, I will look, this is very quick. Usually it's a thing. We see first of all that the file size has been, let's say, increased quite significantly. And this is no wonder because instead of 4 tasks, 8 tasks have been not working. And hence, instead of having just 4 ranks or 0 to 3, we have now 0 to 7. And I was steering this outside the C code, which is now the important learning experience with this. And of course, it's scalable if you want to do this again. Let's say, we submit broadcast. We could also, of course, think about maybe going for 12. And I think then the message is clear. So, and as there's no surprise, again, the size has been doubled, and also no wonder why, because now instead of, we have now much more again from these processors, right? So it has been not really doubled. I just see, of course, but this is something where this is an interesting aspect to see that, again, we can steer from the outside with this job script here the amount really of processes working on it, while the source code remains the same. Right, so this was already, let's say, 4 examples that are all in itself a bit trivial. So I hope you're still with me in all of that. Think about that, of course, when we simulate this over time, like race cars or so, reactions, there's much more information that you want to exchange maybe between different parts of the application, between the different processes, right, over time. And of course, then also the whole aspect of the simulation will be not only, let's say, a small program, it will be run for a long time. We discussed also the SVM, that you don't, should program this as an iterative send receive. In other words, an iterative point-to-point communication, what you could do, of course, but it does not really is efficient. So we have done these things. We have played around a little bit with the task per node. And the last couple of minutes in this lecture today, I want to demonstrate sort of 2 important concepts. And one of it is this interesting parameter that you see here with the time. And I think I go directly to the practicals to show you when we have a practical lecture. It's also beautiful. I called that a little bit sleep. And this is loaded from 2 perspectives, this example. So firstly, we have something which is inherently in the C code, like here, the sleep seconds, right? I've put that now to 20. So this is a parameter which is really within the C code, meaning when I change this, I really have to, remove the executable, or in other words, do an MPICC. And now I can do this because essentially I've already loaded the modules. Otherwise I would now load again, OpenMP and so on. But here I don't need it. And because I already had done this before, if you remember. And when we now compile this, we have the executable again, and also with this 20 sleep seconds hard-coded right in the source code. Now, the concept I wanted to explain you today is this hard-coded example, but also this parameter here. We call it the time, or the wall time, really, until the job is crashing literally into the wall and said it stopped, right? So this is a kind of idea of explain this a little bit. So when you basically run a simulation or application on these systems, you usually have to also specify this time parameter. So how long is your application going to run? This is an experience parameter that over time you will notice, you will experiment, and will find out that this needs a couple of hours. Hence, there's a possibility of giving hours, minutes, seconds. In our example, we stick to seconds, but think about that this is an important parameter also for the schedule overall. So think about all the different jobs of all the different users. By having this information, essentially the scheduler can work quite better, right? And can see, okay, this job, and you see this kind of interesting diagrams here as an example, show you then the length of the job, or at least the expected length. Of course, it could be that the job is earlier done. Right? So this is sort of not really hard-coded in stone that it needs to be exactly this time until the job finished. So maybe, especially in larger programs, it's really hard to determine. Or in other words, when you run 24 hours, you maybe do 25 hours in the job script just to be sure that the 24 hours are really, properly done their computing until the end. And this is now an interesting part. If you remember, we have said 20 seconds as sleep. So there's nothing done. It's a kind of a strange, admittably, application that we want to do. But that's the point of understanding now when we change later this parameter. So I can do sbatch and submit it. We have the job ID. We can go to SQ this time because essentially you see that the Morris job, the Hello Sleep on Newton, is running, right? On compute 1, how much, of course. Here is now the point that essentially we do nothing, we sleep, but for the scheduler, the application is running. So it's a proper application, and of course the scheduler has no idea that there's just a sleep inside. However, what the scheduler is very aware of, and this is now the learning experience, is this time, right? So we said this job has just 20 seconds. And after this 20 seconds, he will cancel the job, right? And if my application is not done then, it's still in the queue processing, then it will be deleted and canceled, basically. So you see that a little bit that now, when we now go to our one that we had was WOSI 77, if you remember, this one here. So let's look into the output. What's happening is that essentially they're going to sleep now and just awake. This is a little bit like here the source code that you see here. So we have this kind of processors that can, if only one reports here the hard-coded sleep seconds, just to make the difference also to our example now. Then we say which rank we are out of how many sizes, and they're both going to sleep here. And of course, also going then afterwards awake when we have performed the sleep. So in other words, we see from the output in the practicals that this was working. So essentially, they both go to sleep and they both are awake now. So hence, what would happen now if we do the following? If we would say, hello, sleep, and 100. Now, many of you will know the answer now. I was just explaining it. But here's it also now, no. Here's is now also important to think that, we have changed the source code, right? So hello sleep.c, we have this 120 inside. Hence, we have to remove the executable because this was a hard-coded 20-second sleep that we don't want now. And to do this again, we have to do the same procedure and compiling it again because the hard-coded 120 is inside. In order to make now the difference, we have, sorry for that. So let's see. And here we have our executable again. And now we will sbatch it. And you remember we don't change anything in the job script. Hence, if we verify it, it is still on 20 seconds, right? So this is a little bit now the tricky part, and would say, well, that is not really working, because the application now runs with 120 seconds in a sleep, while our job script says, well, you have just 20 seconds. And we can observe this a little bit, right? If you look here, seconds go by, 8, 10, maybe 14 now, 16 now, 17 now, 18, job is still running. You see a little bit over time, but this has something to do with the environment. And when we now wait a little bit, we basically will notice a couple of things. That firstly, this kind of job here will have an output, but the output will also look different probably, because I could not finish my job. So nobody was really, let's say, awake. Hence, when we now look into this, we see hard-coded sleep seconds 120, and hello world, I am 1 out of 2, I going to sleep, but nobody woke up. And the reasoning is, of course, that the job was actually running against the wall, right? So it is stopped. In the SQ, it still looks to be there, but the point is that after 20 seconds, actually the job has been cancelled, and will also essentially will write this into the job script later. In the job outcome later. Basically, if we repeat this command, for instance, here now, when the scheduler has done all its business, you see essentially here, compute 1 error, job on cancelled at some specific time due to the time limit we put in the job script, right? So this is also an important part now to understand, that if you do large applications in large computing centers like you see here, you usually have to also specify the wall times here, or the time that your job runs. And if you specify this wrongly, let's say, then it can be that your application, as it is suggested here, is running against the wall, as we say. And this is really all I wanted to present you in the first part of the MPI examples. Quite, let's say, simple examples, but I think for beginners of MPI, still lots of elements to digest. We actually continue with some more examples with non-blocking communication and communicators, and with applications in the next part after some break. See you then.